Hello, everyone. We are moving into our second unit here, which is about the derivative. And so this is lesson D1, D4, derivative. So we're going to start here by reviewing average and instantaneous speed. So we learned already that speed is equal to the rate of change of position. The equation that you know from past classes, right, for speed is equal to distance divided by time, right? The division there makes it a rate, and when we write it like that, we're really referring to the average speed. We've talked about how velocity means speed with direction. So, if you're going up, then your velocity might be plus 10 meters per second if we define up as positive and down as negative. If you're going down, your velocity might be negative 10 meters per second, right? The speed for both of those would be just 10 meters per second, but the velocity has an SIGN attached to it. Okay, you know that the slope on a distance time graph measures how fast the distance is changing with respect to time. So the slope then on a distance time graph is the velocity. And in general, the slope on any graph is going to represent a rate of change, a rate of change. Slope is a rate. Average rate of change, which we call AROC, describes change over a period of time, right? There's always going to be two times. What is the average rate of change between t is equal to 5 and t is equal to 10, right? So it is the rate of change over a period of time, and that makes it the slope of a secant line. Instantaneous rate of change, or IROC, describes the change at a moment in time. So that would be what is the speed at t is equal to 5 at just one specific moment, and that is going to be the slope of a tangent line. For those of you who might know a little Latin, secant comes from the word secare, or cut, that is to cut in Latin. Tangent comes from the word tangere, which means to touch. So a secant line is going to cut the curve at two places. A tangent line is just going to touch the curve at one place. So graphically or visually, if this is the curve, this might be my position with respect to time, then this red line would be a secant line. It cuts the curve at two places, and looking at its slope, we know the rate of change over a period of time, in this case 1 to 10. If you're talking about a specific moment in time and you do this tangent line, which just touches the curve at t is equal to 5, that then gives us the instantaneous rate of change. Okay, so let's do example 1. Pause the video and see if you can figure it out, and then let's check what you think. Okay, so the graphs of the position function for two runners A and B are shown in the figure. The runners completed a 100-meter race and finished in a tie. So always looking at the graph to notice what the y-axis and the x-axis say. In this case, y-axis is position, s in meters, x-axis is time, t in seconds. Notice the scale on the two graphs. This graph on the y-axis is going up by 20s, which means at this ending point on the graphs, my position is 100. It was a 100-meter race. And we look like we're finishing that in 2, 4, 6, 8, 10, 12, 14 seconds. So when we talk about part A, what was the average speed of runner A over the entire race? Average speed on a line is just the slope of the line. So it's going to be 100 meters, that's the distance, divided by 14 seconds, that's the time. And if you do that as a decimal, it's 7.14 meters per second. What was the average speed of runner B over the entire race? Now, Runner B is not going at the same speed throughout the race, but his average speed is going to be the same thing as the average speed of runner A. It's going to be, we are thinking of on this blue graph, right? If we're talking about average speed for that entire length of time, we're taking the beginning and the end and connecting those in a secant line and finding that slope. So for runner B, again, I would do 100 minus 0, which is 100, over 14 minus 0, which is 14, and I would come out with the same average speed for the two runners. Were they both running at the same speed throughout the race? No, they were not. The runner A was running at that exact same speed throughout the race, but runner B, you can see that runner B started out running slower at the beginning and then faster and faster. The slope on that blue curve is increasing as time goes on. So no, they were not both running at the same speed. Approximately at what time was the distance between them the greatest? Well, if this is a distance time graph, right, then you can see they started at the same spot, right? They started at 0, 0, and they ended at the same time at the same spot. But in between, the distance between them is really just the distance between the two graphs, right? So it looks like that is reaching a maximum somewhere, I'm going to say around 8.5 seconds. Somewhere in here, it looks like the distance between the two graphs reaches a maximum. So this would be approximately at 8.5 seconds. Approximately at what time was their speed the same? Okay, now this goes to the instantaneous rate of change. So the instantaneous rate of change on the line is just the slope of the line. The instantaneous rate of change on the curve is the tangent line slope. So we're imagining these tangent lines that are being drawn, and we're saying, where would the tangent line on the curve have exactly the same slope as the slope of the red line? And again, I'm going to say it's somewhere here around 8.5 or 9 seconds. We're just estimating, so you were just going to look at this and go, roughly here, it looks like the two graphs would have the same. The tangent on B would equal to the slope on A. So somewhere around 8.5 seconds again. Okay, so that just is to remind you about average and instantaneous speed. Let's see if we can watch this animation that shows us how the secant line becomes the tangent line as we bring the 2 points of the secant line closer and closer together. Okay, so I have a little secant to tangent animation that you can watch. I recommend that you just go to YouTube at this link and watch this video. It shows you how with the secant line slope, as you bring the 2 points closer and closer together, in other words, as you bring the second point closer and closer to the first point, the secant line becomes the tangent line. And that's just shown really well in that video. So go ahead and watch that video. Let's move on though to okay, so here we have the equations for the slope of a tangent line and the slope of a secant line. The secant line is the AROC, the slope of that is the AROC, and the slope of the tangent line is the IROC. So if we think about a function f, and you think that you're at some specific point A on this function, then the point is A comma f of A. That's where we're at. And remember, f, this right here does not mean f times A. It means the y value at the point A, right? So just keep that in mind as you're looking at these equations. F of A is a y value. If you move to another spot close to A plus h, right? So we're some distance h away from the point A. Then you have a point on the graph, A plus h, comma, f of A plus h, right? That would be my corresponding point on the f graph. So now if I connect these 2 points with a straight line, then the rise over the run, the y2 minus the y1 over the x2 minus the x1, right? y2 minus y1 over x2 minus x1 would give me f of a plus h minus f of a. That's the difference between the two y values. And you just get h on the bottom because a plus h, which is your x2, minus a, which is your x1, just leaves you with h. So that equation, f of a plus h minus f of a over h, is the average rate of change. The instantaneous rate of change, we know, happens when you bring in the second point closer and closer to the first point, and you keep on doing that secant line difference quotient. Keep on doing that calculation as you bring the second point closer and closer to the first point. Well, the second point is h away from the first point. So if you're bringing the second point closer and closer, then effectively you're taking h to 0. And that's why we have this limit statement, right? The limit as h approaches 0 of f of a plus h minus f of a over h. That is in fact the slope of the tangent line, right? So as you keep doing that process, as you saw it in the animation, the secant line becomes the tangent line. Okay, so we've got our two definitions. You've seen this before. And then I just want to show you another way to write the second one. There are two ways to write the slope of the tangent line. And it's just in this last equation, instead of calling the 2 points a and f of, sorry, a and a plus h, the x values, we're going to call the 2 points a and x. So then if you think about the graph, the first point is at a, f of a as before, and the second point though is now x, f of x. So if you write the difference quotient using those letters, then you're going to get a slightly different equation, which means the same thing, but the letters are different. And if you bring the second point closer and closer to the first point, then that's like bringing x closer and closer to a. X is the second point, a is the first point. So these are equations that you want to understand what they mean, and you want to memorize them, but memorize with understanding. Okay, example 2 says find the average rate of change of f of x equals x squared between x is equal to 1 and x is equal to 10. It's an average rate of change. We're given two x values. All we have to do is f of x2 minus f of x1 over x2 minus x1. So the average rate of change is going to be equal to f of, this is x2, this is x1. So it's going to be f of 10 minus f of 1 over 10 minus 1. And please get in the habit of writing that step out so that it's really clear to the reader what you actually did, right? So then f of 10 is 10 squared or 100. F of 1 is 1 squared or 1. And so we're going to get 99 divided by 9 or 11 for our average rate of change. Find the instantaneous rate of change of f of x equals x squared at, notice that we're not over a time period, we're at a specific moment or a specific x value, at x is equal to 1. So now we have to do a limit calculation, right? So we're going to say the limit as x approaches 1, right? The point we're interested in is x is equal to 1. So we're going to write the limit as x approaches 1 of f of x. I'm using really that second definition. I'm using this definition. And let me explain that. So our first point, the point that we're interested in, is 1 comma f of 1, right? This is like our a in the equation up here. So a is equal to 1. So if I write that equation, I then get f of x minus f of 1 over x minus 1, okay? So f of x is x squared. So we're going to work with the equation x squared minus f of 1, which is 1. And then I have x minus 1 on the bottom. And you guys are experts at doing a limit like this. You all know that if you put in 1, you get 0 over 0. And you all know that that does not mean that the limit is a DNE. It means that you have to do some more work. And that work is very simple in this problem. It's just a factoring. So you factor, you cancel, and you get 2 for your answer. Okay? All right, now this next part C is super important. One of the main things we're going to be doing in this unit is writing, actually throughout the course, is writing the equation of the tangent line, right? We know that the tangent line slope represents the instantaneous rate of change. So the tangent line is a very important line in calculus, and we are going to need to be able to write the equation of the tangent line, in this case to the function f at x is equal to 1. Well, it's actually really simple. Just remember that for the equation of a line, you need a point and you need a slope. The slope of the tangent line is the instantaneous rate of change, and that we already just calculated in part B. It's equal to 2. The point that we're at, well, here's the x value of the point. That's 1. The y value of the point, well, we're on the graph of f of x, so the y value is f of 1, which in this case is 1 squared, or 1. Okay, so we want to find the point and we want to find the slope, and then we're going to use the point slope form of the equation. Y minus y1 is equal to m times x minus x1. That's a line equation, right, in point slope form. And your m is right here, your x1 is here, your y1 is here. So very straightforward. Y minus 1 is equal to 2 times x minus 1. You do not need to put this into slope-intercept form unless the question specifically asks you to do so. Okay, I just want to give you a quick visual of what you actually did in this question, right? Notice that this question, x squared here, f of x equals x squared, that's nothing other than the parabola. Y is equal to x squared, the parent parabola. If you are at x is equal to 1, which is where we were for most of the questions, what are we doing? Well, in part A, we went from x is equal to 1 to x is equal to 10, and we drew a secant line, right? And we found the slope of that line. That was the 11 that we found in part A. For part B, what we did is we did a limit process, which means that we are thinking about bringing that second point closer and closer to the first point until the secant line became the tangent line at x is equal to 1, and we found that the slope of that tangent line is equal to 2. And the last part of the question, we simply wrote an equation for this tangent line, and that's what was y minus 1 is equal to 2 times the quantity x minus 1. So that's what we've been doing in that whole problem. Okay, example 3, very similar problem with a different function. Find the instantaneous rate of change, the IROC, for the square root of x function at the point x is equal to 4. So in this case, let's even start with the visual. You're doing a square root function. So remember, 1 goes to 1 and 4 goes to 2. And we've got this shape like this. This is my square root function. It's a parabola on its side with the bottom half cut off. And we're finding the instantaneous rate of change at 4, which means we're after the slope of that tangent line at 4, 2, right? So right here, notice the tangent line goes through the point 4, 2. It's the only point that is common between the curve and the line is 4, 2. Okay, so what do I need to do? Well, instantaneous rate of change means I'm going to do a limit. I'm going to do the limit as x approaches 4. This is my a. I'm using this equation up here again. Actually, let me just write that equation down for you. I'm using m tan is equal to the limit as x approaches a of f of x minus f of a over x minus a. A is the point that you're at. We're at 4, so a is 4. So f of x is the equation. So rad x minus f of a is the square root of 4, or 2. And then here I'm going to put x minus 4. So I've got this little equation. I have to do a little limit calculation. You put in 4, you get 0 over 0. you realize that you either need to rationalize or you can factor the bottom. Let me do it by factoring the bottom just for fun. You can factor that bottom into rad x minus 2 and rad x plus 2, and then you can cancel one of the factors, and so we're left with an answer of we can now put the 4 in, and you get 1 over square root of 4 plus 2, which is 1 over 4. So that kind of makes sense looking at the graph, that the slope of this looks like it's less than 1, and it is in fact exactly equal to 1/4. The slope looks like it's positive, so all of that checks out, and our answer is 1/4. The tangent line equation in part B, well, we need a point and we need a slope. Pause the video and see if you can write down the point and the slope. The point is 4 comma 2. The slope we just calculated is 1/4. So y minus y1 is equal to m times x minus x1, m times the quantity x minus x1, and we get y minus 2 is equal to 1/4 x, quantity x minus 4. That's our answer. Okay, so all of this leads us to the first big hurrah of the course, which is that we have just been calculating derivatives. I'm sure you've heard of the word derivative. It's one of the two big words of calculus, the other being integral. The derivative at the point is called f prime of a, right? So the point is a comma f of a, and the derivative is called f prime of a, the derivative at a point. The slope of the tangent line is what we mean by the derivative. So the slope of the tangent line at a point x is equal to a is called the derivative and is written as f prime of a. F prime of a, take that back. The derivative of a function at a number a is the slope of the tangent line at that point a comma f of a. Okay, so I'm just repeating myself, but here now we have our two equations. F prime of a, you'll notice these are the exact same equations that we had on the other page for the slope of the tangent line. However, we're going to start calling this thing f prime of a instead of saying m tan. Okay, so let's go ahead and calculate f prime of negative 2 for f of x equals x cubed. Okay, so notice it didn't say find the tangent line slope at negative 2. It just said find f prime of negative 2, right? So you have to realize this means m tan at a is equal to negative 2. That's what we're after, okay? So I have to do a limit calculation, right? So f prime of a, I'm going to use this equation. F prime of a is equal to the limit as, actually we should say f prime of negative 2. A is equal to negative 2. F prime of negative 2, limit as x approaches negative 2 of f of x, which is x cubed, minus f of a. F of a, f of negative 2 is negative 2 cubed, or negative 8. So x cubed minus f of a is x cubed minus 8 over x minus 2. Okay, be careful with your signs. So we're going to get x cubed plus 8 over x plus 2. If you put in negative 2, you get 0 over 0, but you know that that doesn't mean the limit doesn't exist. It simply means you need to do same opposite always positive. So we're going to just factor the top and the bottom and cancel the offending factor. Offending because that's the factor that's making the top and the bottom 0. Now that we cancel them out, we can just put in negative 2 and we are going to get an answer, I believe, of positive 12. So f prime of negative 2, which means the slope of the tangent line to this graph of x cubed at negative 2 is equal to positive 12. Okay, and then it said, oh, find the equation of the tangent line. Well, now, so I'm doing this piece right here, right? So the point is negative 2 comma negative 8. the slope is the derivative f prime of negative 2, which is 12. So y minus y1 is equal to m times x minus x1. That's the slope of the tangent line. Okay, let's see what the next problem is. Find an equation in example 6 of the tangent line to the graph of y is equal to h of x at x is equal to 3 if h of 3 is negative 2 and h prime of 3 is negative 1, right? So we are talking about some graph h. We're not given the graph equation, but we are told that we're at x is equal to 3, right? So it's like our a in this equation, or in either of these equations. A is equal to 3, so the point that we're at on this graph is 3. H of 3 is negative 2, so the y value at that point is negative 2. So we've got the point. The slope of the tangent line at that spot, right, is the derivative, which they gave us. So the slope is negative 1. So if I want to write an equation of that tangent line, then it's just y plus 2, that's the minus minus 2, is equal to negative 1, that's the slope, this is the m tan, or the derivative, times x minus 3. Okay, so that's the answer there. It's just a matter of getting used to recognizing that if you're given h prime of 3, you're being given the slope of the tangent line at the point 3 comma h of 3. Okay. Example 7, we're sketching the graph of a function. Now this goes back to Unit 1 where we did some of this in the asymptotes lesson. You were given certain conditions and you had to sketch a graph that matches those conditions. These are actually really good problems, so good to really understand these. Sketch a graph of the function where all these different conditions are met, right? So it's about looking at this and realizing, these first few conditions here, these are points. All of these are points on the graph, right? Points on the function. G prime of 1 equals G prime of 3 is 0. These are tangent line slopes on the graph, right, at specific points. G prime of 0 equals G prime of 4 equals 1. That's also tangent line slopes on the graph. G prime of 2 is equal to negative 1, another tangent line slope on the graph, right? These right here, the limit of G as x approaches 5 from the left goes to infinity, that is a vertical asymptote. The limit as x approaches negative 1 from the right is negative infinity, another vertical asymptote, right? So you want to first know what all of this stuff means, just translate that in your mind, and then you can invent any function. There's various answers to this problem. The point is to make any function that satisfies all these conditions. So these points right here, they're telling you g of 0 is 0. That means the graph goes through 0, 0, right? So place that on your graph. G of 2 is 0. So that means that the point 2, 0 is on your graph. So place it on the graph. G of 4 is 0. That means the y value at 4 is 0. So place 4, 0 on your graph, right? I'm going to draw the graph in red, and the graph has to go through those points. Okay, so we're done with the first piece. G prime of 1 equals G prime of 3 equals 0. Okay, these are slopes. These are slopes of the tangent line on F at x is equal to 1 and x is equal to 3, right? So at these two places, the slope of the tangent line is 0. So if you think of what a 0 slope line is, that's a horizontal line. So if I have a graph which has a 0 slope at a specific place, then the graph looks like that, right? Or like that. In other words, I'm at a spot where I'm at the top of a valley, top of a hill or bottom of a valley on the graph. So we just find one, and you can kind of go to any height you want because it didn't specify how high or low we have to go, but we know the graph has to do something like that there. And then if you go to 3, then the graph has to do something like maybe, it could go up to another hill, but I'm just going to make it do something like this here, right? So I have to go through the point and I have to do that. And again, this is showing us that the tangent line slopes here at 1 and 3 are 0. Okay, next one, g prime of 0 equals g prime of 4 is equal to 1. So you can come to 0 and 4 and draw sort of a slope of 1. So 4 and 0, right? We can draw, that doesn't look quite like 1. It should be about 45 degrees. So something like this, right? 1. And then when the graph goes through those 2 points, you want to make sure that the tangent line looks like it's got a slope of 1. So here we can go through, like this, and then just passing through at a slope of 1, roughly. And then over here, same thing like that, so that it looks like if you drew a tangent line at that spot, the slope would be 1. And then we have to do our 2 asymptotes. As we approach 5, we want to go off to infinity. So just put 5 here, and then we want to just draw a vertical asymptote at 5 and send the graph off to infinity. And then I think it was at -1, we want to draw another vertical asymptote. That's not very nice. Let me do that better. Okay, and then we want this graph here to not touch the vertical asymptote, but rather to go down to -infinity like that, right? So this would be one graph, right? So I'm just going to put these slopes in here of the tangent line so that you see that we've tried to meet those conditions at the right spots. This would be one graph that satisfies those conditions. I'm sure you could come up with other graphs that satisfy the condition as well. For example, these 0 slopes, I could have done this and then down here and then come back up here and do something like that, right? And that would still have a slope of 0 at 3. You could find different graphs, but these are important questions in terms of knowing what all these statements mean in terms of the graph. Okay, so now that we have introduced the derivative, let's talk about what the derivative might mean in different real-world contexts. So here we have example 8. A manufacturer produces fabric with a fixed width. The cost of producing X yards of fabric is C is equal to F of X dollars, right? So in this, first thing to realize is that X is how many yards you're producing, and C is the cost in dollars, right? And how much it costs depends on how many yards you are producing, right? So first question says, explain the meaning of the derivative f prime of x and indicate the units of measure. So units of measure, we know that the derivative is a rate, right? So we know that the units of measure has to be a division. It's going to be dollars per yard. Okay, that would be the unit of measure of the derivative. And the meaning really is just that f prime of x is the rate of change of the cost when we are producing X yards of fabric, right? So in other words, your cost function, who knows what it looks like, but it might be like you start out, obviously 0 yards means 0 cost, and then as soon as you start producing, you had to have your machines and so on. So maybe the cost starts up here and it goes up linearly, and then once you produce a certain number of yards of fabric, maybe you have to put in a new machine, and then it goes like that. I'm not sure, I'm not an economist, but you might have some different cost function which depends on paying your workers, building your machines, buying the raw materials for producing the fabric, etc., right? So what we're saying about f prime is that if you are at any specific x value on this graph, f prime of x tells us at that specific number of yards what is the rate at which the cost is increasing or decreasing. What is the rate of change of the cost at the moment when you are producing x yards of fabric? That's what f prime of x means. Explain the meaning of f prime of 1000 equals 9 in the context of the problem. Well, this means that if you are producing 1000 yards of fabric, then at that specific in that specific situation, the cost of producing, or let's just say the cost is increasing at a rate of $9 a yard, right? So in other words, let me change this graph so that we don't have a jump at 1000. Let's just say that the graph is doing something like that, right? This is your cost versus yards. Then at the situation where you're already producing 1000 yards, the slope of this tangent line is 9, right? So that's telling you that the next yard of fabric, if you will, is going to cost you $9 more to produce that. Okay, that's the idea. Which is likely to be greater, f prime of 5 or f prime of 500? So here it's going to the idea that in economics we have something called economies of scale. So the more you're producing, probably the less the next yard is going to cost, right? In other words, the graph in economics probably going to look something more like it's going to be steeper to start with, and then it's going to slow off because of your economies of scale. So if you're out here at 500, f prime of 500, the slope of that tangent line is going to be less than f prime of 5, the slope of this tangent line. So that's would be likely to be greater would be f prime of 5. And then you can say because of economies of scale. Okay. Last example. Let D be the national debt measured in billions of dollars at time t measured in years. The table gives approximate values of this function at selected times by providing year and estimate of the debt. Estimate the value of D prime of 2012 and indicate the units of measure. So this, by the way, guys, is just a table estimate of an IROC, and you have already done this. D prime is the IROC, and you're looking at a table. You're trying to estimate a secant line slope from a table. From a table you can, you're trying to estimate a tangent line slope from a table. From a table, you cannot get an exact tangent line. You can only get the slope of the nearest secant line. So you come in here and you figure out 2012 is between 2010 and 2015. So we are going to do a tangent line approximation right there to estimate D prime of 2012. It's approximately D of 2015. Let's put it that way. D of 2015 minus D of 2010 divided by 2015 minus 2010. That's our closest approximation of the tangent line at 2012. And if you do this, it's going to come out to be 1534.96 billion dollars per year. That's massive. In case you're curious, in 2022, this debt is now 30,900 billion. So that means 31 trillion. Ouch, that is quite a debt. Anyway, okay, so let's see, what are our takeaways? I mean, there's a lot of takeaways here. In fact, I feel like I didn't write enough takeaways, but let's just conclude by saying very important to remember that speed is the rate of change of position. Slope on a position versus time graph is the speed. Average rate of change between 2 points is the slope of the secant line. AROC formula is y2 minus y1 over x2 minus x1. Oh, I see why it looks so incomplete here. It's because there's one more slide, which is right here. Instantaneous rate of change between 2 points is the slope of the tangent line. IROC formula includes the limit, right? So we're going to bring our 2 points closer and closer and do the secant line approximation. The tangent line at x is equal to a is a line that does two things. It touches the curve at f of a f of a. In other words, remember that the curve and the tangent line, right, share this point, share the point a f of a. They share that point and only that point. And the tangent line, so it does these two things. It touches the curve at that point and it has the same slope as f of x at that point. The derivative of f of x at a is written as f prime of a. F prime of a is a number, right, which equals the slope of the tangent line to f of x at x is equal to a, and the equation is the same basically as for the IROC, but we'll write it as f of x minus f of a instead of y2 minus y1 over x minus a. This is the same as the IROC formula. The derivative is always a rate of change, and it means different things in different contexts. And last of all, the idea and the math of the derivative literally made modern science possible, and therefore your learning of the derivative is worthy of a gong moment, which, if you are in class, you will experience. Have a fantastic day.